Differential equations 4.1, 4.3, second review assignment. Let's take a look at the very last type of problem. These are the most recent types of problems where we have linear homogeneous differential equations with constant coefficients. And what we can do is assume that y equals e to the mx is a solution. What happens when we do that? Well, we'll have m squared minus m minus 6 is equal to 0. You don't have to show your derivatives and plug them in and cancel out, divide out, and e to the mx. It's pretty much understood that you will get a quadratic. And this quadratic, of course, is going to factor. That's m minus 3 times m plus 2. And using the zero factor theorem, of course, we can say that m minus 3 is equal to 0 and m plus 2 could equal 0, leading us to m equals 3, m equals negative 2. What do we now know? We actually now know that y would equal some constant times e to the 3x plus a second constant times e to the negative 2x. And while we're at it, we can say, well, that means that its derivative using the chain rule will bring down a 3c1 e to the 3x. Can bring down this negative 2, we could say a minus 2c2 e to the negative 2x. Obviously, the derivative of that inside function of negative 2x, you multiply by a negative 2. I just brought that out. But look, we've got y of 0 is equal to 2. That means x equals 0 when y equals 2. We had y prime of 0 equaled negative 1. That means when x equals 0, y prime equals negative 1. Let's set up a system and see if perhaps we can find C1 and C2. What do we have? Well, your y is going to be a 2. Here's e really to a 0 power, which is a 1, isn't it? So we have 2 is equal to C1 plus C2, because these are both 1s. Coming over this way, we're going to say that y prime is negative 1. And here, again, we'll have e to a 0 when we plug that x value in. And here, again, we've got e to the 0. Those are just 1s. So we've got negative 1 is equal to 3c1 minus a 2c2. And now what? Well, we're going back, guys, actually to really just going back to your Algebra 1 days, where you had a system of equations. This system, of course, you may solve with your 89. It's kind of silly to do that. I'll tell you why. You're going to do it faster by hand. To cancel out a C2, you've got a negative 2C2 here. I'm going to multiply my first equation by a 2. 2 times 2 is a 4. Here we'll get 2C1. This is plus a 2C2. And this is going to be a 3. And we have a 5C1, so C1 is 3/5. But look, 2 is equal to C1 plus C2. If C1 is 3/5, we can very quickly solve for C2. We're almost done, guys. 2 is really going to be 10 over 5. And of course, you can subtract 3/5 and see that you'd get 7/5. So I have a C1 and I've got a C2. Remember, up on top, I'm going to highlight this in blue, really to make it pop out. You can say, hey, I know what that solution should be. Y is C1 e to the 3x plus C2 e to the negative 2x. But now I know what C1 is. It's 3/5. And now I know what C2 is. It's 7/5. We just solved for that. And nicely, wonderfully, we are done. Let's take a look at our second problem here. Again, we're going to assume that y equals e to the mx because we have a linear homogeneous differential equation, second order, constant coefficients. That's going to mean m squared plus 2m plus 3 is equal to 0. And guys, right now we're not dealing with an initial value problem, which is kind of nice. We won't have to find our constants. But what we do have to be aware of is when we try to factor this, it won't factor at all. Let's remember the quadratic formula. A here is going to be a 1, B here is going to be a 2, and C, of course, is going to be a 3. And we can see pretty much it's going to be opposite B plus or minus the square root of B squared minus 4AC all over 2 times A. And if we were to just fix that up real quickly, we'd get negative 2 plus or minus, well, what's B squared? Well, that's a 4. We'll have 4 times 1 times a 3. Down below, we'll have 2 times 1. And, as we continue on here, you can see inside the radical, this is really 4 minus 12. That's negative 8. I'm going to continue up here, just write this out a little bit. I hope you know that radical 8 is 2 root 2, but I'm going to take out, actually, an I. And then everything can have a 2 divided out. So wow, would you look at that? That's really what we have for our answer for M. And clearly this is complex. And when we have something complex like this, I hope you remember that the general solution would be e to the alpha x constant 1 times the cosine of beta x plus constant 2 times the sine of beta x. So, what is our final answer going to be? Well, it's e to the negative x, c1 cosine of radical 2x, c2 times the sine of radical 2x. You put parentheses around the radical 2x if you'd like. And that wraps up that second problem. One last one, one final one, and it's a good one to take a look at. Again, we're going to assume that y equals e to the mx is a solution. And that's going to lead us to m squared minus 2m plus 4, m squared minus 4m, pardon me. Just copied that terribly. And this is going to factor into m minus 2 times m minus 2, isn't it? And, of course, you have m equals 2 as an answer showing up twice. Well, remember what happens when we have double roots. We're going to assume that we'll have e to the 2x, but then we'll have x e to the 2x for our second solution. And right now we can go ahead and try to find C1 and C2. To do that, of course, we're going to need to take a derivative because we know that y of 0 is equal to 2. That's very helpful. But we also have information about y prime of 0 equaling 1. So, look, y prime, if I were to take my derivative of my first part here, we have to remember the chain rule. 2c1 e to the 2x. But then what? Here's c2. Let's use the product rule right here. We're going to get x times the derivative of e to the 2x. A 2 is going to come out. And then what? We have to take our derivative of x, which is just a 1. And there you have it. So we have to do some work here to really go through finding C1 and C2. We know that when x equals 0, y equals 2 right here. So y is equal to 2. Here's a C1 times e to the 2 times 0. Here's C2 times 0 times e to the 0. Anything times 0 goes away beautifully, wonderfully. A problem like this is just delightful. You already know one of your constants, C1, of course, would have to equal a 2. And that's wonderful. Then we come over here, and we're going to have to do a little bit of work. Here we know that x is equal to 0, and y prime would equal a 1. So we have a 1 on our left side. Right here we have 2c1. This is e to a 0, which is just a 1, isn't it? Here's 2 times 0 times e to the 0. And finally, we've got e to the 0 right here. Well, that's going to wipe out. E to the 0 is just a 1, so we've got 2c1. And then e to the 0 is just a 1. So, inside this big bracket is just a 1. Well, we're almost done here, aren't we? C1 is equal to a 2, so I'm going to just substitute that in. This is kind of nice. And we have 1's equal to 4 plus C2. That means C2, when we subtract a 4, would be negative 3. So now I know what these two parts of my general solution are. C1 is a 2. C2 is actually this minus 3. And guys, what I'm putting a box around right now is our specific solution. It not only satisfies the differential equation. If we took the second derivative minus 4 times the first derivative plus 4 times the original function, you'd get 0. But you also satisfy the initial condition.